the final chapter of this course. And so we've made it to quantum information. And one of the most important things in quantum information that we're going to be using is entropy. So I just wanted to begin by talking a little bit about normal entropy. So what we call Shannon entropy. So this will be 7.1. Now, I'm assuming, well, some of you may well have done some course in information theory, but I want to assume that you don't know anything, okay? So just very briefly go over some important results from classical information theory, picking out mainly what we're going to need to compare when we get to what's called von Neumann entropy, which is going to be the quantum version. Okay, so bear with me, those of you that have already studied some information theory. I will be brief. Okay, so Shannon entropy we can describe in the following way. So if we have a random variable with a probability distribution for the moment, let's just say Pi. So these are the probabilities. It's probability distribution sums to 1. It's between zeros and ones. And then the entropy is going to be is h of x is equal to minus the sum over pi log pi. Now, the justification for this, oh, by the way, just for us, especially since we're going to be going over and looking at qubits, log is always going to be log base 2. Okay, so I'll just write log. In reality, in information theory, you would always put an R here, usually just usually that would be the encoding alphabet, the size of the encoding alphabet. But for us, it's going to be log 2. Where does this come from, this definition? Well, the idea comes from information. So we define the information event. So if an event occurs with probability P, then the information will be I, and that's just some function of the probability. And what the property, the fundamental property we want from our information is that if two events, so if we have two independent events occur with probability P and Q, then we want the information we get from P and Q, so the two events both occurring, to be the sum of the information we got from them both. Okay, so this would be, we want IPQ to be IP plus IQ, and that's just the justification being that the two independent events we sum the information we get from both events occurring. Well, this multiplicative to additive was probably going to be ringing bells somewhere. And you're correct when you think that this is going to be a logarithm, but we have to be, if you have to add a couple of little details. So we assume, assuming I is continuous, 1, 0, 1. And I of, well, let's think about this. What should I of 1 be? So if something's going to occur, I should get no information because the probability of it occurring was 1. So I learned nothing by it happening. So we should have I of 1 to be equal to 0. Okay, so it should be decreasing, since the smaller the probability of something occurring, the more surprise, the more information I get. You know? So the fact is, in this one, if you're right on the right-hand side of the interval, you're getting no information. It should be a decreasing function, so it decreases down to that 0. So I should be decreasing since smaller probability events occurring is more information. Okay, well, with all of these axioms that we kind of make up to quantify this function information, we can now deduce that this implies that I of p is some constant times the logarithm of p. Okay, well, here we can fix the base 2, I guess, because if we change the base, then that just changes the constant. Log of 1 is 0, so that's okay. The only thing we need now is that it be decreasing, so decreasing implies k is negative. As an effect, k is -1. K is -1. So the information IP is simply minus log P. And the entropy, well, that's then the average information where we weight by the probabilities as we would. Okay, so as we should. So the entropy is the average information. Right. Yeah, just that you get. I didn't see your picture, is it? No. Okay. Well, let's just take the example. So take the example, the distribution P of 1 minus P. I'm getting very like deja vu because I've just been doing the information course with the master students. So now I think I've already told them this, but now I haven't. I had to keep reminding myself that I haven't. So that's why I'm frowning sometimes. That's why. So if we had like this probability distribution P1 minus P, then this would be then the entropy would be minus P log P minus 1 minus P log 1 minus P. And you can plot this curve for a probability between 0 and 1, and you get this beautiful thing. So you get 0 and 1, so this will be the p-axis. And if you do this curve here, you get something like that. That should be a half. And if it's a half, we get, well, minus a half log half, which is -1. So we get a half, and the same thing here, which is a half, so we get 1. Okay, so this is the entropy curve. And that compares to all the binary entropy functions. Okay, so this should now be, or will be, emblazoned somewhere on your mind and appearing in your dreams, because we're going to be using it a lot in the next couple of weeks. Okay, so that's well, you'll unpack why I don't get mine in that time at all. Well, the entropy, and in fact, in classical information theory, one of the main results, one of the main aims of information theory is to try and pack as much information into the smallest amount of space possible. So imagine, for example, you're given a picture and you want it to store it. Now, let's just for simplicity's sake, say it's a black and white picture, so we just got zeros and ones. You could just store it every byte. Or what you could do is maybe chop it up into little strings of, let's say, 5 pixels at a time, and work out which. Now, if it happens that you have lots of runs of zeros, because maybe it's got a lot of sky, or lots of runs of ones, because you've got a run of a lump of coal, which would normally happen in a photo, you'll get like these strings of zeros, these strings of ones, occurring more frequently. So with higher probabilities. And the idea with the higher probabilities, instead of storing the string of this, you code it up into something else. Okay, so which will be much shorter. So when you've got frequently occurring strings, you assign to those strings very short strings, and then the infrequent ones, although they may be short, whatever length they may be, you give them long strings, and then you can pack more information in. So that's how you do like lossless compression, which you will see a lot about in JPEG files and all of these things. That's what they're doing. So there's ways of doing this. And so that's one of the main challenges of information theory. Another example might be you've been asked to text. Text is a classic one. You've got a huge text, you want to just store it letter by letter, or maybe the better way to do it is to chop it up into frequently occurring strings and assign the frequently occurring strings very short encoding strings, and then the infrequent ones longer ones, and you can save yourself space and probably money by using a good code. Okay, so these problems have been well studied. Let me just give you a quick example. So let's just say imagine we have a source. Now, source is just going to be something which emits something with probability. Okay, so it emits one of 4 symbols, keep it easy, symbols with a probability. And it's going to be 1/2, 1/4, 1/8, 1/8. Okay, so in the case of the photo, the source would be the strings of 5 bits I get by going from left to right, say, along the pixels. And we could simply encode this, so we could encode this by this symbol goes to 0 to 0, this symbol goes to 0 to 1, this symbol goes to 1 0, this one goes to 1 1. And then we would get our 4 symbols, we would encode something like 0 0 0 1 1 0 1, etc. And then when we come back, let's call these symbols A, B, C, D. We will go, oh yeah, well, this was everything's into blocks of 2. So what the original text was A, B, D, B, etc. Okay. So what we need is this, we need this string to be what we call uniquely decodable. So that we can recover the information that we stored there. So we can recover our information. Now, in this case, that's easy because we assigned, let's call them code words, these strings to each element, each element coming out of the source. And all of these strings have the same length. So to decode, we could go through chopping, and clearly that's going to be uniquely decodable. We exactly know how to do it. But if we try to be a little bit clever, and I'm trying to chop one of these off here, then suddenly we wouldn't know it. So instead, if we tried 0, 0, 0, 1, 1, 0, and I put 1 here, then when we get to a 1, this strings could be, it could either be, A, D, A, D, or it could be A, C, B. Okay, so that would not be uniquely decodable. Now, one way to get around this uniquely decodable is to always use a prefix code. So a prefix code is one in which we always use the same prefix. So we never assign, so in a prefix code, we never assign a code word. Well, we never assign in which some initial part is another code. String is well, that's strange. What am I doing wrong there? Of course. So here you see, this is not a prefix code. I'm just trying to see that the prefix code is always uniquely decoded. I couldn't see why this was a prefix code, but this is not a prefix code, of course, because here, this 1 is a code word here. Okay, so this is not a prefix code. So a prefix code is always uniquely decodable. So let's think how we could get one here. So the idea is to, instead of using this one, which was rubbish, we're going to try and do a prefix code in which we only put this one with a 0, and now we can start all the others off with a 1. So here we put a 1, 0, and then 3, right? Yeah, then a 1, 1, 0, and 1, 1, 1. Okay, now I can uniquely decode any string. If you tell me anything, so if it goes 0, 0, 1, 0, 1, 1, 0, 1, etc., then I can uniquely decode that because I know if until I get to a 1, I know what to do. Yeah? I mean, if this is 0, then that must be the A. This must be A. Now I get to a 1, and I see how many 1s I've got for the next 0. If it's only 1, then it must be the D. Now I get 0, so that's a D. So now I get 1, 1, and then I get 0. So that must be the C. And now I can put a 0 here. And then it will be B. Okay, so this is uniquely decodable because all the prefixes are different. Okay, so you just go until you end up with a code word. And you know that you can't, that must be it because there's no other code word which has that prefix. Now, how much space are we using up? So how should we calculate how much space we use up here? Well, we should weight the length of the string by the probability. So the average, what we call the average word length, is the sum of PI, LI, where LI is the length of these things. Okay, so here we have LI is 2, 2, 2, 2, and here LI is 1, 2, 3, 3. So in this example, the average word length is going to be 2, obviously. But here, it's 1/2 plus 2 times a quarter, which is 1/2, plus 3 times 8 plus 3 times 8. And if you add all that up, you get 7 divided by 4. So now we've seen that we can choose our assignments here in such a way that we can use up less space. Okay, fractionally less space from the 2 to the 7 and the 4. What's this got to do with entropy? Well, let's calculate the entropy of this probability distribution. So the entropy is minus a half log a half, minus quarter log a quarter, minus twice 1/8 log 1/8. Now I chose these probabilities nicely so that we can do the logs. You see, this is just a half. This is minus 2, so I get another half here. This is minus 3, so I get 2 times 3/8. Oh, so painful. Let's call this. Oh, that's complicated, doesn't it? So let's just call this L. Now, the first big theory you prove information, which I won't go into, otherwise doing a whole class, and it's not really what we're going to be interested in. But what Shannon's Neumann probability theory says is that this average word length L, no, it's not true. First thing you prove is that this average word length has got to be at least the entropy. And the non-proof version of that is saying, well, since when I coded everything up here, I lose no information. I can always recover the information. So it cannot be that I can code it up in a way and get less than the average information. It must be more. Okay, that's the non-mathematical proof. But you can, I'll leave that as an aside. You should be able to prove that. Straight. Okay. So the average word length is at least the entropy. And I mentioned then Shannon's noiseless coding theorem. So let me just tell you what that is. Yeah. So you can think of, here I got lucky. Here I have probability distribution in which I can code it up and get to equality here. But that's not always the case. It's very easy to come up with probability distributions in which you cannot reach the entropy. But if we allow ourselves to make semi-source, so that if S is a source, with probabilities, oops, let's set pi, then we define S squared to be a source with probabilities pi pj. Okay, so we take any two probabilities and multiply the gain. And that gives us another probability distribution. Etc. So you can come up extending the source to S to the n by taking sets of n probabilities. So for example, if the probabilities again were p of 1 minus p, then this was S, then S squared would be p squared, p minus 1p, okay, this will be the probability distribution for the product source. And what Shannon Lewis's Polian theory says we can find optimal encodings of S to the n, in which the average word length L satisfies L divided by n goes to hx. Okay, so where x is this initial, the entropy on the initial probability distribution. Okay, so that would be the first couple of lectures. To get there would be the first couple of lectures in the classical information theory course. Okay, but as I said, we don't really have time for that or really need for that in what we're going to do. But I thought I should mention it as to why the entropy is fundamental to these problems in information theory. In fact, it turns out that the entropy also comes into the Shannon's other big theorem, which is when you have a noisy channel. So in a noisy channel, you have two sources, and this is relevant to what we're about to see. So, and this will be happening a lot in the quantum world as well. So we'll have two different probability distributions. Now, in the classical information theory, we often think of one of those as being the source of the stuff that we're going to transmit. And we transmit these things over a noisy channel and receive something, and what we receive is the other source. So we have an input source and an output source. Okay? Now, when we get to quantum entropies, we will often be, for example, comparing the, I guess by now you've worked out that the probability distribution is going to come from a density operator, right? I mean, that's where the probability distribution is going to come from. And you're going to have, for example, comparing the probability distributions between, for example, a density operator before a measurement and after a measurement, things like this. So we're going to see these kind of comparisons of probability distributions. Okay, but I have to say that when we get to the quantum world, things are a little bit more complicated. Okay, but I think that's why it's very important to go through, in case the classical case, which is now the easy case, which is not easy at all, but it will get a little bit more complicated. So let's take our time and do the different concepts which we're going to find in the quantum world, in the classical world first, yeah, the things that are important to us. Okay. Okay, first up is going to be relative entropy. So we're going to consider two probability distributions. And now instead of trying to use Qi and Pi and Qj, it's going to be convenient for us to think of it in terms of probability distribution on the same index. So we'll do let P of x and Q of x be two probability distributions defined on the same index, which I suppose we could horribly call x. Yeah. So x runs through in the same that horrible way that we write down I for to be the basis. Right. So what would be the relative entropy? So the would be and what we're trying to do here is get a measure between how close these two distributions are. So, and here it's important that I write two lines because one line is going to be something else in a minute. So this is going to be, and now it's kind of almost what you think. It's going to be the minus the sum over this x, p of x. Okay. Well, let me just expand that a lot, and then I'll prove the theorem, and then we'll see why this is different. Okay, so this is minus the sum of p of x log p of x plus sum of p of x log q of x, and here we have basically the entropy of the p of x distribution here. So when we get to the quantum world, this theorem is going to be extremely useful and extremely important, that the relative entropy is always non-negative. And it's going to be equal to something we have with equality. If they're exactly the same. If they're exactly the same probability distributions. And the proof goes something like this. A lot of these proofs at the beginning of entropy are based on the following very, very simple fact. That if you draw a curve, well, that's meant to be log x. So here we have x, log x. Then the tangent at that point there is the line y is equal to x minus 1. Okay, when x is 1, y is 0. When y is 0, when x is 0, y is minus 1. So this is the curve y is log x, this is the curve y is minus 1. And so from this we deduce that log x is less than or equal to x minus 1. Let's write it here. Let's do that. Log x is less than or equal to x minus 1 with equality. And if x is 1. Well, you could almost see the proof now. Can you see the proof, Adrian?
Yeah, I already knew it beforehand, so.
Oh, almost. Okay. Well, actually, this is not true. Then you should have corrected me, because this is what.
I know it like using Jensen's inequality, or I don't know if that's like it's one step like the expectancy of the log is greater than or equal to or less than or equal to the log of the expectancy or something like that.
Probably back on campus or something. But anyway, yeah, we will need such things later. At the moment, we just need the fact that this is true. We have to write this as, yeah, we need it to oh, we can do it here. It's implies log x log 2 and now it should be okay. Okay, so now we just so here we have the minus some px log px qx is less than or equal to 1 over 2 Oh, I did it all the wrong way up. Oh, thank goodness for that. Now I see it's all the wrong way up because it doesn't work. Okay, so you should have corrected me.
So it flips, no? Like if you put the minus in, you already have it flipped, and
maybe it's that. Is that what the minus? It's now correct. Yeah. So I've had a minus. I should have had the minus twice in it.
Yeah, like it's P over Q, and then
Is this right?
no. Like it was right. It was right the first time, I think. And then when you put the minus, you already have the expected value of the log. Like it was right the first time.
Yeah.
Yeah, you're right. It was right the first time. So here, I just need to get rid of minus. So that's the rentable proof. Now let me just see where I've got my sign the right way and the wrong way. No, I think it was wrong. I think it was wrong. This should be minus C and this should be minus. Yeah, no, it was wrong. So it was, this should be minus entropy. So this should be positive, this should be negative. Which means it should be this. You're right. So I was right first time. Yeah. Which is minus.
Like it's minus P over Q. Like when there's no like when it's an expected value, there's like the P should be at the bottom.
How's that?
Ah, wait. Minus P. Yeah, now it's right.
That's right.
Yeah, I think so.
Yeah. So we've successfully proved that this relative entropy is indeed greater than or equal to 0. So now we just have to think about the case what happens when we have equality. And we've got equality here. If we have equality on this curve, so using this inequality here, so equality occurs if for all x, well, what would it be? It would be that this value here was exactly 1. Yeah, so q over x divided by p over x is equal to 1, which is what we wanted to prove. Okay? So if one of these inequalities wasn't exactly inequality, then it wouldn't be inequality overall. So since we've got inequality overall for every x, this thing here is equal to 1. Well, this has a very nice property, which we will use a lot, and that is that the entropy, therefore, is related to the logarithm of d, where d is the size of the index. And to prove this corollary, what we do is we now put in Q to be equiprobable distribution. So let Q of X be the equiprobable distribution. So that means Q of X is equal to 1 divided by d all x. So let's skip just down, try and work out where to stick to. We can skip to here, can't we? Oh yeah, and I should say this x then, where x is the random variable with probability distribution Ex. Okay, so if that is then the one with the PIs, then this is minus h of x. And here I have minus the sum of p of x logarithm of 1 divided by d, so I'm going to x. So I get minus h of x. And I've got a sum. And that's possible. Minus 1 of the log d, summing up the probabilities is going to give me 1. So this is minus h of x plus log d. And now we'll use the fact that this is greater than or equal to 0 from the theorem on the relative entropy, and we have that the entropy is at most log d. And also we have that with equality, so also with equality, you can only have d of x is equal to 1 divided by d of x. Okay, so we also know how to get to that. We have a bound on the entropy, and it's maximized when it's equiprobable every possibility. And that comes back to our idea of this being information, because if we have a completely equiprobable distribution, then it's giving us as much surprise as possible. Yeah? We have no bias over what's suddenly going to appear from the source. It's all equally every time. Okay, so that's measuring there. Yeah, so this relative entropy, let me just do one more little quick example. Just to see that this is what it does, it compares. See, let's imagine that the P's were well, I don't even know, P of x naught is 1 minus epsilon, and P of x1 is s. Yeah, so you're getting x naught with almost, I'm assuming epsilon is very small, so this is a very large probability. Here you have a very small probability, but on the other hand, this is very small and this is very large. How does this relative entropy transpire? Well, according to this line here, let's take it from here. So the relative entropy is going to be, well, you get epsilon log epsilon plus 1 minus epsilon, 1 minus epsilon here, which is on our curve that we saw before. Yeah, so this is just on our entropy curve that we drew before. But then here we get minus epsilon log 1 minus epsilon minus 1 minus epsilon log epsilon. And it's this final term, of course, which dominates everything when epsilon is small. Because when epsilon is small, the log of epsilon is going to be almost negative infinity. Okay, so this is going to be approximately minus, let's say, tending to minus infinity as epsilon tends to first. Yeah. So they're extremely getting further and further apart. So the relative entropy can, and if you put the minus on, can then go off to infinity. Okay. So I have one more thing on classical entropy, and then we can get to something new, which for those of you who have already done information theory will be a bit of a relief, I imagine. So let me do this one more thing that we're going to need, and then we'll be on to Neumann entropy. Back to our joyous Hilbert spaces, density operators, measurements, and all the things we've grown to love over the last couple of months. Right, 7.3. Conditional entropy. Okay, so what we're going to do now is we're going to have two random variables, x and y. Be two random variables. I'm going to introduce some shorthand notation. And let P of x be the probability x is x, B of y in okay, so P of x, y is going to be the probability x is x, y is y, and the probability x condition y with the probability x is x, y is y. Okay, just going to use that shorthand notation, otherwise we're going to get into a bit of a, it's all going to become a bit of a mess. So observe the P of x, y in this notation is P of x, y, P of y. Well, that's supposing, of course, yeah, so I'm also supposing that P of y is probability y of y. Now, this joint probability distribution here, what is it here? This is also a probability distribution, so we can define the joint entropy to be the entropy of this joint distribution, like that, and the conditional entropy, or we can do both of those, but this. And again, with some over x, y, with the probability for the joint distribution of the probability of the conditional one. Yeah. And from this, we can prove that the joint entropy is equal to the conditional entropy. Okay. And the proof should be just sticking this into here. Okay, so let's stick it straight in. And now we just use the log, expand the log. And now when we sum, here we have the conditional entropy. So let's continue here. So here we have the conditional entropy hx conditional y, and here we can sum over the x's. So this will just give us the sum of the y's. So summing over the x's, these probabilities here of x is equal to x is just going to give us the probability that y is equal to y. Okay, so that's here because this is the entropy of y. So one way of interpreting this is to say that, well, in general, you can think of entropy as a measure of uncertainty. Like it's bigger when you've got an equal probability distribution, and then we've got the maximum uncertainty possible. So you could think of the same thing here and say, okay, well, what this is saying is that the entropy h of xy is like the uncertainty is which is left once we know y. Okay, so you see, you learn everything that's about y, and you take away from that, and what you get left with is the entropy of x, knowing y. And so you can think of it like that. And an important observation here, so since this is certainly positive by definition, and here, this is by definition, all the terms in this side are negative. So this is, we have which in some sense makes sense because we're more uncertain about the joint distribution of x and y than we are about simply y on its own. X can only make things worse and make things more uncertain. And this is an important thing to note because we're going to see when we get to entropy in the quantum world, this is not necessarily going to be the case. Okay. And if you want to hint why that is, think about a Bell state. Okay, almost there. One last thing, which again, well, a couple more things which we will see within appearing again in the quantum world. We need subadditivity. So subadditivity will hold. So what we're going to find is some things hold and some things don't. So this is subadditivity. So that one is one of the ones which won't. This is one of the ones that will. And we should, there is a very short proof of this. Yeah, so we just look at this sum, here x, y, log p of x, p of y, divided by p of x, y. Again, as before, that's less than or equal to 1 over log 2 sum of p of x, y. And now I can replace this by the same thing minus 1. And now you see what happens when I sum. This first bit is cancelled with this, and I think the third two, which has got to be 1. And here I just get the sum of all the pxy's, which is 1. So I get 0 again. So it's the same proof as before.
I mean, can you just say that it's just the conditional entropy of p of x times py and p of xy, like the product of the marginals and the joint? Like this is already like a conditional entropy, no? Like that's why it works. So the same thing again.
You're saying it's the same?
Yeah, it's a conditional entropy between two distributions.
Probably. So yeah, you just repeat. Okay. You're just replacing. Yeah. Anyway, probably. So that's it. Yeah, because now I just expand this side and we get this is equal to first one is h of x y, and then when we sum over the x's we get minus h of x minus h of y. Okay, so yeah. And the final thing, which again will be very important for us, is the mutual information. Which is going to be the sum of these two entropies minus the joint one, which, as we've just seen here, is something positive. Okay, so that's proving that this is positive. And this measures the, well, it's a measure of how much information x and y have in common. And to see this, you can note the following, that the But the mutual information, if we now substitute in the fact what we had before, which was that this was basically then h of x conditioned on y, sorry, h of, so this is h of x conditioned on y, so h of y minus, which is just, so if this was 0, so this is kind of the way to look at it. If this is 0, then that implies that h of y is equal to h of y knowing x. So knowing x, we know nothing about y. We're still as uncertain about y as we were before we knew it. So knowing x, we learn nothing about y. And that corresponds to what? There's no mutual information. You have to want the information in the file. And likewise, we do by this. So knowing y, we know nothing about x. Now, in that case, if you have an input source, if you think of x and y as your communication again, you have the input source and your output source. What that's saying is, if you're trying to use that as communication, you're putting it in here, and they have nothing, they have no mutual information, then you can't use it. Okay, this channel is just too noisy. Too noisy. What Shannon's theory says is that if that channel has some mutual information, these two random variables have some, you can choose them in such a way that they have some mutual information, then you can use that channel to code with a probability tending to 1. However simple. Okay, that's Shannon's noisy coding theory, as opposed to noiseless. Okay, well, I hope you have, those of you who haven't studied information, graphical information theory, at least interested in it now, and know and have some idea of what it's about. Yeah, on the other hand, we can look at, we've had maximized here. So on the other hand, what would be the other case then? So that this is 0. So if h of y and x is 0, and then the mutual information is everything as uncertain as you have as y, then this is knowing x, we know. Or say y is determined. Which is either maximal. So whatever information there is in y is the information there is there. So there's a lot of information. Okay, and this, in the case of communication, is the perfect situation. Yeah, so you've got everything you're sending, you lose absolutely no information, and you get exactly all the stuff at the other end. Okay. We have made it a little bit longer than I thought it was going to. We have made it back to quantum mechanics and the von Neumann entropy. A bit of water. Okay, let's get it off. Right. I think it's a fairly natural definition. So we already saw in quantum mechanics a density operator replaces the ideas of probability distribution. So we define the entropy. Or density operator. So a density operator, if you recall, was a positive operator. So a positive operator of a trace. One, okay, that trace being the sum of the probabilities. So going back from if we're given a density operator, we have to be a little bit careful because it's not a unique decomposition. We proved that a long time ago now. But it does have an orthonormal basis of the eigenvectors. So we know. So it's we know. So rho is diagonalizable in an orthonormal basis of eigenvectors which have to say positive. Yeah, well, we can ignore the okay, let's say non-negative. It doesn't make any sense. Non-negative eigenvalues. So this rho has this decomposition. We are now going to use these probabilities okay. Now, I saw that diagonalizable things, especially positive things, allow us to take exponentials and logarithms, and all these are positive, then we can take logarithms. So this implies that the logarithm of this density operator is simply log p I. Now, there's a very fancy definition, which is going to end up being the definition you thought it was going to be. But let's do the fancy way. The Van Neumann entropy then is going to be Neumann entropy. It's going to be minus the sum of log. Oh, sorry, missed the trace. That's some trace. Minus the trace. I mean, I also did this out, but okay, and let's prove now that that is exactly what you think it is. So this is minus the trace of rho, which is the sum of pi. And the log of rho, which is the, let's sum over I and j here, and have log pj, j. Now this is over the same orthonormal basis. So this I and j is going to be delta I and j. So here we're going to get minus the trace sum over I, pi log pi I. And now if we recall that with a trace, we can trace does not depend on which orthonormal basis we use. So we can use this orthonormal basis and trace over that.
And the logarithm doesn't depend on the basis either. Did we prove that, or
Sorry?
like the logarithm doesn't depend on the basis either? Did we prove that at some point? I don't remember. Like it doesn't depend on the basis, which you just then take the.
We always define it on the basis of eigenvectors, normal orthonormal basis of eigenvectors.
Oh, and that's unique. Maybe. Yeah.
And so we can trace over, which basically just means we then get an extra sum here. So k over k sum over I pi log k. And since where this is in this over the same orthonormal basis, and so this is going to be minus the sum of pi log pi, which by now should be beginning to look rather familiar. So it is exactly what you think it's going to be. And at this moment in time, we're kind of thinking, well, everything's going to be the same, right? Because all we've got is a classical entropy. And that's kind of true. So it's just the classical entropy that we get from the eigenvectors, eigenprime parameters. So here's an example. Here is, I claim, a density operator. Now, it doesn't look like it. And that's the thing about density operators. You can't see that they're density operators per se. Well, I say that. You've got some good indication, actually, thinking about it, but let's talk about that now. Okay, there's my attempt at a density operator. And let's see that, let's really see that, well, first, in matrix form, this would be this is 1/2 minus a quarter minus a quarter. So the good news is the trace is 1. Okay, we can just use the old add up the things on the diagram. We see the trace is 1. Now, is it positive? Well, we need to find out what its eigenvalues are. So so it's a quarter minus a 16th, probably 3/16. And I'm guessing that 3/4 of 1/4 because I've got a 17 and multiply to get 3/16. So they're both positive. So this is positive operator. It's a density operator because the trace is 1. These are the probabilities, 3/4 and 1/4. So we have that. So the entropy of this density operator is simply 3/4 minus something. And you can probably simplify this thing now. 3. The log of 1/4 is going to be -2. And this is going to be -2 again.
So I do say it's 2 minus 3/4 log 3.
Yes. And this turns out to be approximately 0.81 something 112.128. So as you can see, it's fairly uncertain. Okay, this would hit 1. This would hit 1. Recall if we had half, and it's somewhere along that curve that we saw before, like here. So you see that's about roughly 0.8 up here. Okay. Right, so now I'm going to take a little bit of time to prove the very important relative entropy results. And this is really going to be terribly useful for 2 major results in this section. Firstly, we're going to be comparing, for example, a density operator before measurement with a density operator after measurement, and then compare the relative things. And it so happens that what we're going to prove is that the entropy increases with the measurement. Okay, so that's one result. And the other one that we want, which was trivial for entropy, almost trivial for entropy, is that this Van Neumann entropy satisfies subadditivity as well. Okay. Now, at the moment, we still haven't got quite clear how to define the corresponding concepts of relative and conditional entropy. Okay, and so that's what we have to do now. Yeah, so I'm going to start off with 2 density operators. And the relative entropy is going to be and in a way, it's what you think it's going to be. So it should be this. Right? So what we have to do is we're going to have to stick in all the things on the logs and see if it turns out to be the same thing. And it's not quite as simple as simply combining the 2 probability distributions that we saw in the classical case. Okay, so this is known as the Klein inequality. And again, we've got the equality thing. So the equality You can only get the same. Okay, so we have to just be brave and put everything in and see what happens. Okay, at some point it will get a little bit tricky. Okay, so we start off with the orthonormal, just the orthonormal decompositions of these two things. Now I'm going to confuse. I hope that I don't confuse you here, and maybe I should. Is it going to be okay if I use J for the eigenvectors of sigma, or do you want me to use some psi's and phi's and stuff?
I would not use, like, put some subscript.
You want
Like-
something?
Yeah.
Okay. All right. I mean, yeah, you're right, because we've already used a factor in 7, and now I'm going to use it for the different. So let's call these ones size, and these ones phi's. Okay? Right. So let's write down the definition. Well, the first bit we've already done, right? I mean, we already worked this bit out. So we have S of is equal to minus pi log p. Because we already did that thing. And now we've got a trace. So do I want to do it straight here? Yeah. So now I'm going to sum over some orthonormal basis, and the one I'm going to use is this one. Okay, so we use this one. That's going to be the i's of the ket. I should have the ket there. Trace of rho. So let me write in my moment. This will be another piece. What do I write in the value? No. Okay. That's good. So I don't like anything. Rho, because otherwise I'm going to have a problem with the indices, but we'll see something nice happens. Okay.
Well, yeah. I understand that the two operators have the same dimension, do they?
The two
Operators, density operators, rho and sigma.
they're both on the same. They're both operators on the same Hilbert space.
Okay.
Yeah, but it doesn't have to be. Yeah, could be. Yeah. Okay, now, what is this bit here? Let's just look at here. So let's do that. So if I bra this, sorry, I kept this with a phi I, which of course in this side would be J, all of these are going to be zeros. The only thing I get left with is a pi and the kets of the no, the bra. So this comes in there, it kills this ket and leaves me with the bra. Okay, so that's one thing we need. So that's going to allow us to switch this around here. So let's do this. So this is now, do I just substitute in? No, I don't. Something else this. This should have been positive, right? Because this is the logarithm of the probability. Did I get that wrong before? Did I put the How did I define the random entropy? Because I should have defined it as minus, yeah? And I missed out the minus, I don't remember now. This should have been minus the trace of this. Did I get this out? So this was there's a bit of this. Okay. Well, if you calculate this, you get this. Okay. So I'm not sure you might go back and check whatever I wrote before, but it should have had a minus sign at the front. Yeah, so this is so far, this is this trace, this thing is equal to this. Okay, now, also, let's think. So this we're going to flip down the other side. Well, let's do this one. So we have this is equal to sum of pi log pi minus the sum of pi. And now things looking a little bit nicer. We've just got this log sigma. So now we could actually we can substitute in here. We can just substitute that straight in. So just put qj phi j. And we should still have on the other side. So now this side is the I and j. And you let me get away with this. This is the log. That's the log thing. But you see, this is just a number, so this can now come out. So we get the sum of pi log pi minus the sum over I and j of what I'm going to now call pij. And here I get pi log qj, where this pij is so this is good, almost there. Now, notice that if we sum these pij's, so note the sum of pij over I, that's just taking the trace. That's just now taking the trace of this thing in here. Okay? But this thing in here, with respect to that basis, is nothing, I mean, it's just like a 1 on the diagonal and all the others are zeros. So this is just going to be 1 if we sum over I for all j. And likewise, pij, if you do the other p, you just switch these two out the other way, and you get this is 1 for all I. Okay, so now we can use the concavity of log So by quantity of log, which is maybe what Adrian was referring to before, we have that the sum over j of Pij log Qj is that equal to the sum of Ij. Which we're now going to complete. We are going to completely call. Sorry, I should put the sum starting. Yeah. This is the log of the sum, of course. Okay, so now we're going to do this log of r. Okay, so that's the big step. But that's going to, so all that does, what that allows us to do is change this von Neumann entropy kind of thing into a classical, so into the classical case. Okay, so this was the big step. So this was when we do this using the concavity of log. Now, of course, this just becomes when I do the less than equal sign. So let's still got this. So Pi log Pi, and now I've got minus log. And I think I want, of course, this is negative. So presumably I should be choosing this one the other way. So, but we already proved this proof, so and now what we've got is a classical relative entropy. So we proved that this is just a classical relative entropy, which we proved is greater than or equal to 0. So it only remains now to have a look. So that proves that this thing is indeed greater than or equal to 0. And now I need to look at the case of equality. So in the classical case, where we had relative entropy, we had equality for only these two distributions were the same. So in classical case, we have equality if now if Pi is equal to Ri. But what was Ri? Ri is equal to this side of the chart. Okay, so if we're going to have this as always equalities, we need that Pi is equal to Q of sigma I, but not sigma, maybe tau I. For some commutation. I this Pij is a permutation. So recall from down here, we proved that the sums in the columns were sum to 1 in this matrix, this big P matrix. And so, well, up to a permutation then of the indices and the bases, rho and sigma are the same thing. Yeah, because also for that you need to use the backwards. So the zero one matrix would be unique 1 in each row and column. Yeah, but what was PIJ? So actually, to prove the things you've done, indeed, there's one more step which I forgot to write down my notes there. PIJ was, and I don't have this again, because I was doing it, you will have to remind me. So let's try it this way around the line. So this implies then that, so this is 0 and 1, this implies that are the same basis. On the same basis. So the only thing up to and we have finally showed that these two density operators, in the case of equality, are the same. So, in a way, what we should be realizing from the difficulties of that proof compared to the classical case is the eigenvectors somehow have a role. Okay, it's not simply the probability distribution. There's these relative entropy then is also dependent upon the scalar product, let's say, between these the orthonormal bases. Okay, so the PIJ is here. This is going to depend on how close, how the angles between the vectors in the orthonormal basis. Okay, so that's one thing. That's relative for Neumann entropy. Next time we're going to be seeing where does the conditional come from, and the idea there is going to be that we have the main x-y distribution will be a density operator on composite system A and B, and then the x and the y are going to be the ones you get, not always, but in this case, you're going to then define the density operator of the entropy of the reduced density operator when we trace out the B and get the row A. Okay, so we're going to be doing that and comparing these. And in that case, also we're going to see that it doesn't work the same way as it might do. So at the beginning, it looks like, oh, well, it's exactly the same. We just get the same entropy of the probability distribution of the density operator. But when we start trying to do these conditionals and relative things go a little bit wrong. Okay, things go a little bit different, but more interesting. And we're going to see some very nice results that come out of that. Okay, so I don't think I want to try and prove anything else today because I'm getting tired after my 2 hours. So next time it will be that we'll be looking at the entropy of distributions of density operators to begin with, and then we'll go on to composite systems. Okay, but that's going to be, let me stop the